All right, welcome to lesson 3.2b, where we're continuing our discussion on least squares regression lines, LSRLs. And as a reminder, that is the kind of new phrasing that we use for lines of best fits. And at the very end of last video, I got into a little bit of like why we make that distinction. The idea, again, to review what we talked about at the end of last video, when you make a line of best fit for a problem, every point has what's called a residual. And the residual is going to be the distance between that point and the line and the prediction that we made. So this distance right here would be the residual of that point. Points that are below the lines, below your line of best fit, have a negative residual, and points above have a positive. And basically what we want to do is we want to be able to combine all of these residuals and make that kind of combined total as small as possible, because small residuals means our predictions weren't off by very much. But if we add them straight up right away here, all of our negatives and positives are going to cancel, much like we talked about with standard deviation in the last chapter, or a couple chapters back. So what we do instead is we square the residuals so that they're all positive quantities. And you can see that in this picture right here. Visually, you square each residual by showing a literal square. And what ends up happening if you do a line of best fit, and like you're trying to decide, do I tilt it like this or like this or like this? You tilt it in the way that makes the total of these squares as small as possible. And that is why we get the name least squares regression line. So that's an LSRL's main idea. Now, as we progress in this chapter, we'll learn a little more about where that, how you make a line that does that. We're talking about one piece of that here, though, in today's slides, and that'll be right here. So I got to kind of explain what's going on in this picture and teach you just one piece about a least squares regression line. So if you look at all of these different dots right here, each of these dots has an x coordinate and a y coordinate that makes the ordered pair. If you were to take this point's x coordinate, this point's x coordinate, this x, this x, this x, and you averaged all of those x values, so you take the x from every single point, you end up getting this x mark right here. So the symbol I would use for that is x bar. So if you add the x coordinate from each of those points, that ends up being right here. And then if you do the same thing, but now with the y coordinates, I'd take this point's y coordinate, this point's y coordinate, this one, this one, this one, each point's y coordinate, and you average all of those together, the average of all the y coordinates is going to be at this height right here. So this is the average of the y coordinates. And the purpose of this illustration right here is meant to show you that this spot right here, it's not an actual coordinate from our data set, but that point would be considered x bar, comma, y bar. And the important thing about that point is it's on our line of best fits. So the least squares regression line, this wasn't like a formal proof or anything, but it's just meant to illustrate for you guys. Anytime you have a least squares regression line, it has to pass through the average of the x's and the average of the y's of all your different coordinates. Okay, so kind of a valuable thing if you have a little table of points and you want to know something about the least squares regression line, you can take the average of the x's, the average of the y's, and that point will be on your line of best fits. Okay, now you guys remember from algebra class that you need 2 points to make a line. This only gets us 1 point. We'll talk more about the specifics of this like later on. For right now, that's at least one thing I wanted to get across though. Now, the next slide right here is going to talk about how you find a line of best fit on the calculator. Because generally in AP Stats, what tends to be the theme with this class, we don't really worry too much about the nitty-gritty doing the math ourselves. We let technology do that part for us, and then we focus on understanding and interpreting things. Similar idea here. It's a lot more likely that you'll use the calculator for the line of best fit than it is that you would have to find it yourself. And you actually learned how to do this back in Algebra 2 with me. There's just a couple little twists that I need to talk about here. So the steps are there, and this table of data is from our first lesson in the chapter on the long jump and sprint distance problems. So we've seen that table before. First thing you have to do to make sure that R appears on your calculator. In Algebra 2, I would have just fixed your calculator for this, but you can follow along. But this is like a one-time fix. If you go second and hit 0, it'll take you to the catalog, which is literally a command of like a list of every command in the calculator. And keep scrolling or go to the D section of the catalog. There's going to be an option called Diagnostic On. If you hit enter and enter again, it'll just say done. That's what turns R on your calculator. So if your calculator doesn't show you R when you do the linreg stuff, just do Diagnostic On like that. So what you do is you go stats, edit, like you guys are used to from seeing this in Algebra 2. And I went ahead and typed all of my X's in L1 and all of my Y's in L2. So all my data is already in the calculator from this little table on the side. Once your data is typed in, you quit out, you go back to stat, you go over to calc, which means you're going to go right arrow to get to this tab right here. Now, back in Algebra 2, we just chose linreg ax plus b, choice number 4, and that's the one we used. It's not like you couldn't use this one, but remember that in AP Stats, we like to have the constant first and the slope second. So it's a plus bx. And actually, there is an option for that later on down in the list. It's just number 8. It wasn't visible at first. So generally, I like to choose this one for AP Stats because it has it in the right order, not mathematically wrong, won't lose you credit if you choose the other one. But yeah, I'm going to choose that option here. When you do this, it's going to give you like a little menu right here. My X's were in L1, my Y's are in L2, that's fine. You do not want anything in the frequency list. So if there is something there, you're going to delete it. And one new thing that I'm going to show you right here that we wouldn't have worried about in Algebra 2 is the store regression equation feature. So what you can do is actually store this equation so it throws it in the y equals already, and if you like wanted to graph it or something like that. So the way you get that to be where you want it to be is if you hit the variables button, then I'm going to go to y variables, and then the very first choice function right there, I can choose to throw it in y1, y2, or whatever. This is optional, but it's kind of handy. So I'm going to show you guys how to do that. So again, that was variables, y variables, and then function. So I'm going to store it in y1. I'm going to hit calculate. It's going to think, and it's going to toss me all of this information right here. So it's y equals a plus bx, but then they tell you what a is, and they tell you what b is. Pay attention to negative signs because they can be easy to miss. Your slope on this problem is negative because the b that goes in front of x is a negative number. The correlation r is also a negative quantity. You can see negative 0.83. And that r squared right there, in Algebra 2, I just said ignore that. We won't use it till we get to AP Stats. We will learn about r squared in our next lesson, but for now, it's just a number that's right there. So you can very easily write down this equation with a couple decimal spots. I would say generally 3 is a good number, but don't chop the number too soon as a general rule. Now, I mentioned that y1 thing that I did, that extra step, if you go to your y equals menu after doing it my way, it went ahead and it threw that equation already in y1, which is kind of nice. You don't have to like transfer it yourself. What I'm going to do just to show you that it works here, I'm going to actually turn plot 1 on, which should get me like a little scatter plot, like the data that I have. Let's see if that works just straight up, and I can show you how to fix it if that doesn't. But I'm going to go zoom stats. And I'm just going to see what this does for me here. Yeah, that works out really nicely, actually. So if you ever wanted to graph a scatter plot on your calculator, I didn't do it with you guys in Algebra 2 because it's too many buttons and stuff. I said don't worry about making the graph. But you can see if you go zoom stat, you can see all my dots from the scatter plot along with my least squares regression line. When the calculator does linreg, it picks the line that makes those little squares as small as possible. So this is the best possible line of best fits. So yeah, that's good stuff right there. A little bit of review and a little bit of new in showing you guys calculator stuff. Now, our new topic for this video is on something called a residual plots. And before I bring up the rest of the slide, I want to remind you guys, we talked about this in our R lesson earlier on. Just because R, the correlation, is good or high, doesn't mean your data set is automatically linear. That's an easy trap to fall into. So this little data set that my face is sort of covering over here is a half parabola. It 10 points in it, and the R is a 0.91, almost 0.92, but that data set isn't linear. So just because R is high doesn't mean your data set is automatically like a linear data set. In order to decide if something actually is linear, we use something called a residual plot. So let me show you what a residual plot looks like using these pictures right here. So on the left side, you're going to see just a random line of best fit problem. So we've got our data, we've got a line of best fit going through the middle, and that's totally cool. To make something called a residual plot, we already learned that each point for a line of best fit problem has a residual. So that guy would have a small positive residual, slightly larger negative residual, pretty big negative residual, pretty small positive, etc., etc. Each point has a residual. So what you do when you have a line of best fit problem, you're going to keep your x-axis the same. So this x-axis over here on my residual plot is the same as this x-axis here. Instead of graphing your y-coordinate, though, on the original problem, we graph our price, I guess, was the y-coordinate. What we do is we graph the residual from the y-coordinates, okay? So like this very first dot right here on the far left has almost a residual of 0 because it's almost on the line. You can see right here that corresponds to this dot with a really small positive residual. The next dot has a somewhat bigger negative residual. And there it is right there with its negative residual. So it's kind of sort of like if I were to take that line of best fit from the first graph and tilt it so it was flat, and then just look at the difference to that line. That's kind of what's going on. If you picture that line of best fit being tilted to be flats. So you have positive residuals and you have negatives, and that is going to help us decide if a linear model is appropriate. So what does a residual plot actually do for us? I'm going to move to the next slide right here and show you a better example. So this is another line of best fit problem. This is actually a parabola half again. And if you look at my original data set over here on the left, the line of best fit looks sort of kind of good. Like it's like, oh yeah, that line kind of is close to my dots. It's probably doing a pretty good job. So if you do that process, like I did before, and show you guys again, same x-axis, didn't change between regular graph and residual plots. But if you graph the residuals right here, the first couple points, these two dots are going to have positive residuals. You can see that here and here. Then that guy has small negative, slightly bigger negative, blah, blah, blah. You can see the negative residual points and the positive residual points. What a residual plot essentially does is it magnifies how far off your points are from the line of best fit. And if you look at this residual plot, you would be like, wow, that looks a lot like a parabola. So when you look at a residual plot, it magnifies the differences, how far off our points were. And if you see a pattern in your residual plot, the residual plot points to you, hey, you probably should have used a parabola model for this equation because this totally looks like a parabola. That's what it does for you. So in order for a residual plot, like if we look at one of these, in order for the residual plot to say, oh yeah, the line, that was a good choice, what we would want to see is just a random scatter of points. Because if there's a random scatter, when we magnified the pattern, we didn't find anything better. But here, I tried to use a line of best fit. I was like, oh, my line's going to be great. But then it magnified how far off I was, and it's pointing me to the fact that a parabola or some other sort of model might have been more useful. So what do you do when you look at a residual plot? Random scatter means the linear model was as good as it gets. If you just see a smattering of points like that, the linear model is doing its best. But if you see a pattern, especially a curved high, low, high pattern or something like that, that tells you that another model besides linear might actually be better. And I'll help you guys write that down in the next slide. So on this slide right here, what does a residual plot do? I kind of talked through that for a couple minutes there. It magnifies how far off our predictions are. And if you see a pattern in those predictions and how they're off, that tells you that some other type of model was actually better for this problem. So a linear model is a good fit if the residual plot shows random scatter. Okay, and a residual plot or a linear model is not a good fit if the residual plot shows a leftover pattern. And I have a few quick examples here to close out this video. So I don't know why my animations are screwed up here. This third one is what's going to appear first, I'm pretty sure. Yeah, over here. So if you look at this graph right here, this is just a straight up residual plot. Is a linear model appropriate? I've got points kind of scattered all over right here, and I've got this one dot up top that's kind of making it. So like you could look at this and be like, is this random scatter? Is it not? I would say for this one that a linear model appears appropriate. Oops. So with this right here, this seems to be mostly spread. I don't see a really compelling pattern in this problem. So a linear model would be appropriate for that one. So you can say linear appropriate right here. The next example also shows just a bunch of points scattered around. I don't see a pattern in that residual plot, so that makes me think that my line of best fit is as good as it gets. So what you can write down for a problem like this is there's no obvious leftover pattern in the residual plot. So a linear model appears appropriate. Okay, and that's all there is to it. So my last example right here is another really blatant one. You can look at this and be like, well, that looks like a parabola. So that tells us that we should consider quadratic models instead. But a way of writing this, and I'll show you a more kind of, this one is a no, because there's clearly a curved pattern. So no, there's a curved, it goes negative to positive to negative pattern. So linear is not appropriate. The linear model is not appropriate. It doesn't have to be this cut and dry either. Like if I were to have a residual plot, and usually residual plots have 0 marked in the middle conveniently, so you can see what's positive and negative. It could be a situation where you've got some points over here, and then they kind of go down like this, where there's a pattern to them, or they could come back up again. If you see a blatant pattern, the linear model is not the best option. You're not asked in AP Stats to talk about what is the best option then. You just say a linear model is not. Okay? So pattern is bad in a residual plot. And if a problem ever in AP Stats asks you to talk about if a linear model is appropriate, you use a residual plot. You do not try to use R or something like that. The last thing I want to do is a little optional quick thing right here. I want to actually show you guys how to make a residual plot on your calculator, but you can choose if you want. This isn't something I would make you do on a test. This is more of just an extra interesting thing. What you're going to do to make a residual plot is you're going to go to edit right here. And when you're over in L3, let me see if I remember actually how to do this because I didn't write it down ahead of time. Pause. All right, so the last thing I want to show you guys is making that residual plot, just so you can see. Again, this is more of an above and beyond thing. I won't make you make a residual plot on the calculator. Usually they'll give you a picture that you can use to analyze. So what you need to do once your data is typed in, you have to actually run linreg. So if you've run your linreg already for the problem, you're going to go up to the top right here to the next column, L3. And then what you're going to want to do is go second stats to the list menu right here. And there's an option that says resid for residuals. If you hit that and hit enter again, it'll populate that L3 with the last linreg you ran. So make sure you run linreg on your data before you try doing a residual plot. So it has all the residuals. So this guy is a positive 3.6. This guy over here is a negative 4.1, etc. And then all you need to do is go to second y equals. I'm going to use plot 1. And then I'm going to go ahead. I have my equation from earlier in there that I'm going to delete. So I'm just going to look at a plot 1. And I'm going to do a scatter plot option, which is this first choice right here. But instead of graphing my x's and my y's, the y's that I want to graph are the residuals, which are actually in L3. So I'm going to hit second 3 on this problem. And once you do that, if you hit graph, and I got to rezoom and everything, so zoom stats, you can look right here. And this seems to be more or less random scatter. There's not like a very obvious curve pattern to this. So that would tell me that a linear model was appropriate for that long jump problem that I was doing earlier. So that's how you would graph one of these on the calculator. You can also go from point to point and see the actual residual. So the y that it shows right there is the residual for each of your dots. So it's kind of handy.